Good. So now what I will do is that I will continue the course with introducing the Markov decision processes that I mentioned last time. So just to recall you this picture, which is in which, so these Markov decision processes are some special kind of Markov chains. Usually they are inhomogeneous in time and with state space, which is not necessarily finite or countable, can be infinite, can be R, for example, or RD. I will give the precise definition in a few moments. And it is, I recall you that you have the state of your, state, or the state of your system at time n is given by xn. So it can represent the various things like the price of some assets, the value of your portfolio, and the cash that you have in some firm or something like that. And then you have some controller, some agent, which can at each step time n, can make some action. Making some action, and by making some action, you would get some reward, which would be in some time negative or positive. So when it is negative, it means that it is bad, and when it is positive, it is good. And this reward would depend on the state of the process time n, and on the action which is performed on the system. And by performing this action, then the new state of the system would be xn plus 1. And then you continue like that. And at the end, the goal is to find what is the optimal actions that you have to do in order to maximize the reward obtained. Okay, this is a picture, and now I will give some precise definition. So I mentioned all these kind of problems last time. Okay, so now I will give the definition, precise definition of what is a finite horizon Markov decision process. So finite horizon is because here I will not consider the case where we let evolve your process for infinite time. I will fix some capital N, which is capital N will be some fixed time, and all the system will evolve during this time window. After time capital N, everything is finished. Okay, so, and we can also consider infinite horizon time Markov decision processes, but okay, it is some other story, and we'll present just finite horizon time Markov decision processes. So let me give now the definition. Okay, the definition to introduce these Markov decision processes depends on several elements. So you need first a state space, the state space of the system in which the state is living. So it was xn previously at time n. So xn belongs to E, which is a state space of your system. And this E is not necessarily finite, it's not necessarily countable, can be infinite, can be R, for example, or RD. And we have this, but in general, it is a measurable space, okay? So this is the first thing. It is a state space. First ingredient that you need in order to define your decision Markov process. Second ingredient is the action space. So it means that I told you that at each time the agent, the controller, has to perform some action. This action belongs to some space, which is denoted by A, like action, and it is a measurable space again with some sigma field calligraphic A. Okay, here this letter is calligraphic E. Okay, it is a sigma field of state space. It is the action space. Here again, this action space can be finite, can be infinite, can be R, can be RD, or can be something even more complicated in some evolved theory. And okay, now at each time n, the agent or the controller have to perform some action, but you can imagine a situation in which the set of action, depending on the time and depending on the state of your system, are some actions are not allowed. If you are in some state, you can do all the actions that you want, but if you have some other state, then yes, you cannot perform all the actions. You have some restriction on the actions. And so it's the reason for which we introduce Dn here, which is a subset of E times A. So E is a state space and A is the action. And in fact, Dn represents all the actions that you can perform if you are in the state space E and if you try to perform the action A. So more exactly, what we do is that for each X, for each state X in E, we define, so X is in E, we define the set of actions which are allowed to do at time n. So the reason there is the n here, because it is actions that you can do at time n, and maybe with time, you are at initial time, you can make all the actions, but with time evolving, you can make less actions, for example. And so it is all these XA which are in Dn. So it is a set of admissible action at time n when you are in state X, all the actions that you can perform. So Dnx is a subset of the action space. Okay, and we assume that, of course, it is measurable in order to have some well-defined theory. Okay, and okay, now what I told you that, you know, when in the pictures I presented at the beginning, you had the xn, then you have some action, which is an at time n done by the controller, and then by the action, you get some new state xn plus 1. So we will assume that in fact is when you perform the action, the state space, the state after the time n, when you perform the action an, is not something deterministic, but is random. So you perform some action, but you have some randomness so that you can pass to some other state with some certain probability. And all these probabilities are encapsulated in some transition stochastic kernel from Dn to E. So I gave you previously in the previous lectures the definition of a stochastic kernel from Dn to E, but it's recalled here. So it is something which is denoted by this letter here, this notation, Qn of B given xa. So x is usually, it is the state in which you are at time n. A is the action that you will perform at time n. And given this state and this action, then you will pass to some new state, which will be random. And this new state, which will be random, will be described by this probability measure, which is written here. It is this application, okay, which is a probability measure. So it means that with some certain probability, with the probability Qn of B given xa, if you are in state X and you perform the action A, you will be in a new state, and with this probability distribution function, which is given by this Qn given xa. And so that is a probability measure, but also to have some well-defined theory in terms of probability measure theory, we need some measurability of this application. So we will also require that if you take some, if you consider this application, which to xa in Dn, so Dn is a set of admissible actions depending on the states that are allowed, we impose that this application is measurable. Okay, it is in order to have some well-defined theory. So this one is just to define all the objects that I will later. And this guy, it gives a probability that at time n plus 1, the state is in B, given that at time n, the state was X, and that the action taken at time n is A. Okay, so this is the third ingredient. And now there is also the reward that I mentioned, that each time that you do some action an at time n, then you get some reward. Some reward will depend on the xn and will depend also on the an. So we describe these rewards by some measurable function from the set Dn, okay, the set where you can of the admissible actions and depending on the state. And it is a measurable function which is in values in R, so it means it is not necessarily positive. So, okay, it is a reward, but you have to think that if it is a negative reward, it means that it is a penalty, in fact. Okay, if it is a positive reward, it is really a reward, something which is good, some gain. And we can also imagine that there is a difference of the reward when you are in the final state, because in the final state, it is finite horizon time n. So it means that at the final time n, you are in the state xn, and now you cannot take any action. The game is over, and so we define some terminal reward, G capital N, would give us a reward obtained when you are finishing your process in the state X. Okay, so maybe just before to discuss about these remarks, let me give you some examples, some representation, some graphical representation in order to understand all this language here. There are several ingredients which are necessary to define some Markov decision process, but in fact, it is at the end, it is not so complicated. So let me give you some, or maybe I can do some new one. Okay, so let me give you some graphical representation of a typical Markov decision process. So graphical representation are difficult to imagine in the case where you have some uncountable a number of states, a lot of actions possible. So I will take here, I will take the case where the state E is just say 1, 2, 3. So finite state space. So you have only 3 states in your system. You have now the actions. So the actions, for example, they are just 0 or 1. And to simplify, I would assume that at each time, Dn, okay, Dn is the set of, you say it is a subset of E times A, which is Dn is equal to the sum over the union over X in E of Dnx, and this Dnx, it is the admissible actions at time n when the state is X. And to simplify, I will assume that this Dnx is equal to A. So it is the same at every time. And for every, if you are in the state 1, state 2, or state 3, you can perform all the actions, 0 and 1. And now, so let me give some graphical representation of, now I will have also to describe, in principle, I should describe what is this Qn, which is a probability transition kernel. I have to describe what is this Rn and what is this Gn. Okay, the interpretation of Rn and Gn is quite clear. So just this Qn, which is a bit more evolved. So, but in fact, imagine that you have these, so you have three space, you have 1 here, state 1, state 2, and state 3. Then you imagine that you are performing the action 0. Maybe this color is not so good. Yellow is better. So action 0, so it means that if you are performing the action 0, you imagine that from 1, you can go to 2 with probability 1/2, or stay in 1 with probability 1/2, or when you are in 2, you are always staying in 2 with probability 1. And if you are 2, you have some probability 1/3, for example, to go to 1, and 2/3 to go to 3. And when you are in 3, imagine that you stay in 3 forever. With probability 1, you come back to 3. So it is, if A was equal to 0, then it will be, you will have just some Markov chain on the state space 1, 2, 3 with this probability. and to phase A equals 0 is associated some probability transition matrix. Now imagine that you are performing A equal to 1. And then if you are performing A equal to 1, you have different probability to evolve. So for example, here 1, you stay with probability 1, you stay in 1. Then here you imagine that, for example, you have 1/2 to go there, 1/2 to stay in 2, and here 1/3 here, and sorry, it is 1/2 here, 1/2, no, so it is not possible. So I say that if you are in state 2, you have 1/2 to stay on state 2, 1/2 to go to state 1. If you are in 1, you stay in 1 forever. And so 3, for example, you have probability 1/3 here and 2/3 here. Okay, it is a graph of a Markov chain. So you have to graph the Markov chain. And
excuse me, what about yellow arrow from 2 to 2, which equals 1? It's odd, maybe.
Yes, you are right. It is not possible. Yes. No, phase 1 cannot exist. Yes, because you have exactly, you are right. No, phase 1 doesn't exist otherwise, because you have 1/3 to go to 1 and 2/3 to go to 3. So I agree, it doesn't exist, sorry. But you see, it is like if you have the graph of 2 Markov chains with 2 different colors depending on the actions that you are doing. If you are doing the action 0, then the probability matrix probability transition is given by these yellow arrows. And if you are doing this action 1, it is given by the violet probability transition. So it means that, in fact, in my you see, if A is equal to 0, so what is this Qn? So here, in fact, I assume that for each n, you are performing the transition matrices here are not depending on n. They are the same for each n. Okay, but you could imagine a situation in which the graph that I did here is for n equal to 0. When n is equal to 1, it is some other graph with different arrows with different values. For n is equal to 2, it is still some different 1. So at the end, it is impossible to make the graph. You have to make a graph for each n. But for example, in this case, where Qn is in fact independent on n, it's equal to q. And so the q, for example, where you are in state 1, this is a state, and you are making the action 0. So you are in state 1. So what is Q1, Q2? Q2, it is you are state 1 and you are performing the action 0. So you have probability 1/3 to go, sorry, you are in 1 and you ask the question, if I go to 2, what is the probability? It is 1/2. Q1, 1, 0 is equal, in this example, is equal to 1/2 also. Okay, it is a probability when you are performing the action 0 and that you are in state 1 to go to the state 1. So probability to remain on the state 1, to stay in the state 1, it is 1/2. You have, for example, Q 1, 0, now 3. Okay, what is the probability when you are performing the action 0 to go from the state 1 to the state 3? You see there is no arrows, in fact, so it is 0. And you see that here I wrote for each 1, 2, 3 because of finite state. So I have only to give the weight of each state, but this is a probability here that I define when you fix this state and this action. For each state and action given, this guy, these 3 numbers define probability, 1/2, 1/2, and 0. And in principle, I have to write it for any value of the state and any action. So at the end, it will give, I have to give you, so for each state, you have 3 choices. For each action, you have 2 choices. So I have 6 numbers to give in order to define completely my probability transition. And so it means that, imagine you start at time 0, you start in the state 1, for example, and then you say, your controller, you say, okay, I would choose to do the action 0 at time 0. So what will be my next state of my process? With probability 1/2, it will be 2, and with probability 1/2, it will be 1. And then depending on the state in which you are, you have some reward will depend on the state, okay? And so if you are initially in 1, you can say, okay, no, I will not choose the action 0, I will choose action 1. If you choose action 1, which is violet arrows, then you will stay in 1, and then you will get some reward. Of course, so it is a graphical representation that you can perform in the case where you have a little set of actions and a little set of states, but otherwise it is impossible to make some graphical representation. But is it clear? So the main point is the interpretation of is a QN. Okay, QN depends on the state in which you are, on the actions that you are performing, give you the probability to jump to some new state.
Yeah, but I think that the notation is a little bit confusing because we write over like state comma action, and then in at the beginning we write state to which we go, and somehow like the state and action come together with okay, so a little bit confusing notation.
Wait, here it is. So here it is a state and here it is the action. So it was before I was defining this Q n, but it depended not on n, of this x a. So it was a state. For each state and for each action, I defined some probability measure which depend on these 2 guys. So
yeah, and it is a probability measure on our initial space of states.
Exactly, which is 1, 2, 3. So
yeah, okay, yeah.
So
I understand this, but it just how you write it. Oh, and this is just.
If you wish, I could write the Q B given, for example, 1, 0 is, you know what is a Dirac mass? Yes.
What?
A Dirac mass? No. Okay.
No,
so
but yeah, but I understand what's going on. Just.
Yeah, it's just it is 1/2, 1/2, 1 2b plus, okay, it is an indicator function plus 1/2, 1, 1b. No, sorry, it is opposite. Like 1b 2, 1b1. So just because I have some probability measure on finite set, so instead of writing like a probability measure, I just give the weight, the probability to be in 2, the probability to be in 1, the probability to be in 3. But otherwise, the general formula is this one. So I don't see where is the problem with the notations.
Well, I understand what is going on. So, okay, thank you.
But I think yes, they are completely consistent with the notations.
Yeah. Okay. It is. Yeah.
Okay, so you have to think that this Q and B given XA give the probability Qn. Okay, so it is Q and B XA is the probability that at time n plus 1, xn plus 1 is in B, given that at time n, xn was equal to x, and that at time n, the action that you took is equal to A.
Yeah, okay. Thank you for this point of view.
Okay, good. So a little bit, so it is all the ingredients, but at the end, just in few seconds, you will see that it is just a Markov chain. It is a Markov chain, but it is a special kind of Markov chain because we have these actions. So what is, okay, two remarks that I will do here. Remark one is that there is a special case that we called stationary Markov decision process. It is when, in fact, you have not so much dependent in n, like in the examples that I show you. In fact, it is a case where, so Qn is equal to Q. So at each time n, you have the same probability to jump from 1 to, okay, if you fix the action, you have to fix the action, but if you fix the action, it is the same law to jump from 1 to 2 or the 1 to 3 and so on. It doesn't depend on time n. And the dn, the set of action, doesn't depend on the time. You have, if initially you were allowed to do a certain set of actions when you were in the state 1, then at time 2, you will have exactly the same set of action will be allowed at time 2, at time 3, and so on. So it's the reason for which it is called stationary. It doesn't depend on time. And it is also the reward does not depend so much in time. It depends, okay, imagine that here the parameter beta would be equal to 1. So it would mean that it doesn't depend on time at all. So it is the same, always the same reward independently on the time evolution. At each time it gets the same reward. But sometimes it is quite for modelization to introduce some discount rate, discount factor beta, because you know it is the money that you have today. It is better to have 100 rubles today than to have a priori. It is better than to have 100 rubles in 5 years, because there will be, so if you have 100 rubles today, you can invest it in the bank and then a priori it will increase, while if you have in 5 years, it is better to have it now because you can create some interest. So to take into account of this interest that you can create by having the money in advance, you have to, usually you introduce some discount factor. Okay, and so these special cases are called a stationary Markov decision process. And okay, there is also some times we will see some example in the exercises that this reward, so here in the modelization that I gave, this reward depend only on the state in which you were at time n and the actions that you are performing at time n. But in some models, sometimes this reward can not only depend on the state in which you are, the actions that you are doing, but also the state in which you will be at the time n+1. So it means that the reward here is depending on x, the actual state, the actions that you are taking at time n, but also the state y that you will get after performing the action A. And so here, in order to encapsulate this kind of situation in our modelization, what we do is that we define some reward, which is some average reward, which is you take this reward Rn prime x a y, but you integrate respect to the probability to jump at time n from x to y when you are performing the action A. And so this give you some average reward, which does not depend on the future state. It depends really on only on the state. So for the moment, it's not very important. I will not consider this case in the theory, just in some exercises. We will see that sometimes we have to modify to think about it, when you have the modelizations, then you have to think how to encapsulate everything in this kind of framework. Okay, good. So please give me some, okay, for the moment I didn't really define a process. I explained with words what is this process, but I didn't define the process XL, the stochastic process. But now I have all the ingredients to define my process. So it is what I will do now. But before, yes, it is not only that, I have also to introduce this notion of actions. So here for the moment, the actions are, I describe the set of actions which are possible. Now we will call a decision rule at time n. We will denote by fn. So it is a function fn, which is measurable as usually, which goes from the state space E. So to each state X, you associate some action depending on the state anywhere. So it is a way to formalize the fact that the controller will perform some action depending on what is seeing, what is the state of the system. And of course, we have to assume that this decision rule Fnx belongs to this Dnx, which is a set of actions which are allowed in your process when you are in the state X. So Fnx is in Dnx. And okay, so we will denote by capital F index n the set of decision rule at time n, and we assume that it is always possible to perform some action, because otherwise the game is not so interesting if the controller can do nothing, doesn't have a way to act on the state of the system. And so it is a decision rule that you perform at time n, and then you can perform this. So you remember that there is some final time in my game. At the time n, everything is finished, the game is over. So I can perform some action at time 0, some action at time 1, some action at time 2, some action at time n, capital N minus 1, and then I will jump to the final state X, capital N, and so there I cannot do nothing. So a strategy consists of a sequence of decision rule indexed by the time 0 until the time capital N minus 1. You perform some action initially at time 1, at time 2, at time N minus 1, and afterwards it is finished. And we call that a strategy or policy, okay? And we call it is, so it is N stage, because later we'll see that we can also consider policies on the time interval small n, n plus 1, n plus 2, capital N. So here it is a complete strategy.
Yeah, but these strategies are specific because at time k, your decision is based only on where you are, not on the history. Yes, so
yeah, exactly. Yes, you are right. It is this. You remember that my model is okay. Yes, it is something. Yes, you are right. This action, in fact, the action that you will take at time n is only a function of the present state. It doesn't depend on the past, and it is a reason for which it will be a Markov decision process. You don't look to all the history, but it exists also some theory like that where you can perform some decision rule depending on all the past. But it is not something that I will do in this course. For me, everything will depend. The decision will depend only on the state in which you are. Okay, but you are right.
So there's a model that can use history of process. How it's called? Just a decision process or what?
No, it is. I think it is called Markov Decision Process with memory or something like that. Okay.
So it's not, but it's not Markov now.
No, it can be in some circumstances. It can be Markov, in fact.
Okay.
But I will not discuss that. Okay, because it's because you can. It is not Markov, but you can make it Markov by extending a bit the space of your process. But okay, I will not consider this case. I will just look at this kind of processes in which we are taking the decision depending on what is the state of the process, and you don't look into the past. But there are many extensions. Here it is just a lecture of introduction to this Markov decision processes, and I cannot present everything. Okay. For example, there is also this theory existing in continuous time, which is where it is more involved in infinite time and with some other thing. Like, for example, here that I put in this remark is that sometimes you don't decide your decisions that you are taking. Here, you see it is completely deterministic. You say you are in the state X, so I decide to do this action. For example, action 0 or action 1. You can also make some theory in which now the action is random. So you are in the state X, and instead to choose action 0 or to action 1, with priority 1/2, you decide to do the action 0. With priority 1/2, you decide to do the action 1. Okay, so it is what is a remark which is here. But again, I will not consider this case. Okay, for me, some policy, some strategy, you are in some state and you decide to do something, and which is completely deterministic. Okay, now it is Markov decision process, because in fact, this kind of process will define with all these ingredients that I have now, I can define some Markov process, which is usually it will be time inhomogeneous process, non-stationary. So what is this process? So what the result is the following, which is a theorem. Given all these things that I gave, so the state space, the action space, the space of allowed actions, the kernel transition, the reward. No, the reward and the final reward are not necessary to define the Markov decision process. But with all this information, you can define some Markov process, which is that you have the following. So the space, of course, of your process is E. And for each fixed policy, so there exists some random variable x0, xn, which are on some probability space. Okay, the random variables are fixed, but on this probability space, you can, for each policy pi, you can define some, and for each initial state x, you can define some probability measure px pi, such that initially, okay, it is notation is here. The probability is that x0 is equal to x is equal to 1. Under this probability measure px pi, is a probability measure would depend on pi, okay, and would depend on the initial state x. And the probability measure when you are fixing this policy pi, given the initial state is x, is that xn plus 1 is in B, given all the past. Okay, so since it is Markov, it has to depend only on xn, which is in the case here, or more exactly to the final state, which is depend only on xn, because here xn and fn of xn, since it is deterministic, okay, it is just something depending on xn. So it is the probability of being in B, given we are in xn, and then you are performing this action fn of xn, as you were saying before. And so in this way, you obtain an inhomogeneous Markov chain on the state E. And this inhomogeneous Markov chain depends on the strategy that you are following. If you change of strategy of the pi, you will define a new probability measure px pi, and you will have some different evolution of your stochastic process in time. Okay. So, okay, you can ask, why does it exist? And this exists because of some theorems that I gave you last time. If you remember, I have to come back to the past. I gave you this theorem of Ionescu-Tulcea. Okay, in fact, we need some weaker version, because here we are in a finite time. So we don't need to consider the process well defined for all the time in small n. But you remember that here it was, so you can use this theorem, is that if you have some probability transition kernel QM, okay, you remember that this probability transition kernel is something which is this QN, okay, is a probability transition kernel on E. So this Qn here was something which was going from okay, Qn from E times, okay, it was, maybe it is written. Yes, it is written here. Here, it is a general definition of a kernel, stochastic kernel. So it depends on X is a state and B is the next state. So it is given that you are in state X, what is the probability to be in B, okay? And you have two conditions. There is, the first condition is that it is a probability, and then it is some condition of measurability. And here, so here it was written in a very general form where this space A and this space E are not necessarily the same. And here it is in the case with a theorem of Ionescu-Tulcea, it was written where the Qn is a stochastic kernel on E. So the A and the E are the same. And then it gives you the existence of some Markov chain with state space E, such that Qn is the transition kernel. So the probability that xn plus 1 is in B given x0, xn doesn't depend on n, and is given just by that Qn B given xn. Okay, this was this theorem which permits to give the existence of this Markov chain. If you are giving me some kernels, stochastic kernels, I can construct some Markov chain with this property. So here it is exactly this theorem that we can apply. But what is a kernel that you have to use? The kernel, in fact, it is the following, because we need some kernel on E. So you define some new kernel, Q tilde n. Q tilde n of B x will depend, in fact, on the strategy that you are following, pi, and will be just the Qn of B given x fn x. And these Q tilde n pi are stochastic kernels, because if you fix x and you see it as a function of B, this Q tilde n pi is fixed, is a probability measure, because Qn is a probability measure when you fix x and A. When you fix x here and the action here, it is a probability measure. And moreover, since Fn is assumed to be measurable, in fact, the function which to x associate Q tilde n pi B given x is also measurable. So it is a well-defined stochastic transition kernel. So you can apply this Ionescu-Tulcea theorem in order to say that this process xn exists. Okay. Is it clear, or there are some questions about existence? If it is not clear, I can repeat, or we can discuss to. But if it is okay, okay. So you have this Markov decision process. In fact, for each strategy, fixed strategy, you are a different Markov process. Okay, each time you're fixing your strategy, and then it modifies as a transition laws to jump from one place to some other place, and this transition depends on time. Okay. Okay, now what I will give is a second interpretation, a second way to see what is a Markov decision process in some sense more probabilistic point of view. So in fact, here it is called disturbance interpretation of the Markov decision process. So here we will introduce some extra random variable living in some extra space, and we will define in the following. So as before, so here we have the reroad, the n step reroad, which is here, the final reroad, which is here. There is this state space here, this action space here, the set of allowed actions, which is encapsulated in this space dn. But I introduced three new ingredients which are given here. There is a space z, okay, it is calligraphic z, this letter. And I have also some new function tn that I will precise a little bit later, and q and z, which is a priority transition kernel of the random variable zn. So what it is? So z is a space which calls the disturbance space, endowed with a sigma field. Okay, it is some special letter. It is some Gothic z. Okay, it is a sigma field corresponding to this space z. And q and z, it is okay. It is a stochastic kernel, but stochastic kernel not in the state space as before, but in this new disturbances space z. Okay, it is so a priority kernel from dn to z. Before in the Markov decision process formalism that I gave you some qn was some priority kernel from dn to e. Now it is dn to z. And tn, which is a third ingredient that I introduce here, is given by the following function. It is a measurable function on the set of space actions, allowed space actions, times the space of disturbances spaces with values in the state space E of our process, and which is called transition or system function. And then what is the relation between this interpretation and the initial Markov decision process is that if I have all these things, then if you have some policy fn, so fn, you remember, it is some function which go from E into A, just that fn x, fn x is in dnx, so you can perform the decision, it is allowed. And you introduce this xn plus 1, which is the evolution of this process is xn plus 1 is equal to tn, this transition kernel of xn, fn of xn, and zn plus 1. So there is some extra random variable here, which is zn plus 1. And the zn plus 1, okay, is this transition. This transition is given by this q and z. And then this define a decision process, Markov decision process. And every Markov decision process can be also, if I give you some Markov decision process, you can introduce this space that you have this relation which is satisfied with some certain space z and random variable. So sometimes this representation is more natural than the other one. Sometimes this other one which is more natural. So we will use these two different interpretations. So let me show that it is equivalent, in fact, to have this interpretation. So there is something which is very simple. It is that if you give some Markov decision process in the setting before, what I do is that I take something completely stupid, which is I take z, which is exactly equal to e, and this sigma field, which is a sigma field of E, and Tnx z is equal to z. So if you look at this guy here, I mean that xn plus 1 is equal to zn plus 1. And for q and z, I just take the initial initial stochastic kernel of my Markov decision process. And then you can check that, of course, I will define the same process in this way by using these, by introducing these disturbances, spaces, and this random variable, and this transition function. I will define the same process. So it is one sense. So if I have some Markov decision process, I can find some disturbances space in which I have this disturbance interpretation of Markov decision process. Now the reverse way, if I give all these elements which are given here, and I pretend that it has defined the process in this way by this equation, then this define a Markov decision process. And this is quite a Markov decision process with which kernel? With the kernel which is given exactly by that. So why? Why? Because you have to remember this relation which is written here. And so you see, so it is written here. So the process Zn plus 1 has follow Qnz Xn Fn Xn. And so since Xn plus 1 is equal to Tn Xn Fn Z Zn plus 1, Zn plus 1, so if you look at what is the probability, what is the probability under this strategy that Xn plus 1 is in B given X0 Xn, it is by definition, it is a probability that Tn Xn Fn of Xn Zn plus 1 is in B given X0 Xn, but Zn plus 1 as for low phase 1. So phase is the same as it is the same as the Q and Z, so that T and Xn, Fn Xn Z in B, which is exactly the Q and B given Xn, Fn Xn that introduced just before, just given blocked, which was given here. Okay, so it is a two different ways to see the same Markov decision process. So maybe it is a bit not so natural now, but I will give you immediately some example where it will be much more clear. So it is the consumption problem. You remember this consumption problem is some problem that we introduced at the beginning. It is this consumption problem. At each time, I have some capital. You have some capital Xn at time n. It is my capital, but the action that I can perform is that I can consume some part of this capital, and so this action is given by some function Fn of Xn. So of course, this function of Xn will be smaller than Xn. So the decision rule. It is typically the set of allowed capitals that I can use for consumption. You cannot consume more than what you have. So this Fn of Xn will be smaller than Xn, and it is this action is just to say what is the quantity that you want to consume. And so what is the state space? The state space is 0 infinity, because okay, you have some positive value of the capital. It is possible capital that you have, and xn is the wealth that you have at time n. Now the set of action, it is a set of wealth which can be consumed at time n, and so it is a priori you can consume as much as you want depending on your wealth. But now D and X is a set of actions which are allowed when your capital is X. If your capital is X, the actions that you can perform, which is the A, so action A is the capital which is consumed. And of course, this capital A has to be positive, but has to be less than X. So it is a D and X, this consumption probe. And now, so what you say in this consumption problem, we say that also you perform some actions on your own. You perform some action by saying what you consume, and but it is more natural to say that, in fact, if you are consuming, so you are removing some part of your capital, xn minus fn of xn. It is when at time n you take some part of consumption, so it remains in your portfolio or in your so in your portfolio it remains xn minus fn of xn. It is the capital which remains, and then after during the time n and time n plus 1, this capital will fluctuate and it will be multiplied by some random variable z n plus 1, which represent the fluctuations of your portfolio. Okay, so it can be increased, can decrease. Zn plus 1 is some positive random variable, and we assume that they are all independent. So it is Zn plus 1 denote the random return of the asset at time n plus 1. Okay, and what you do for the transition kernel, it just feeds this function xn, which is a capital that you have at time n, an, the quantities that you are consuming, and Zn plus 1 represent the return that you obtain during the time n and n plus 1. It is the evolution that you will have during the time interval n plus 1. And so here in this consumption problem, we assume that these Zn are independent non-negative random variables. So this Q and Z will be just the distribution of Zn plus 1, which is just independent of the state in where you are and the action you are taking. Okay, whatever the actions that you are taking, you consume some capital, remains some capital in the portfolio. This portfolio, the capital of this portfolio will evolve according to the rules of the market, but you cannot control it. You are just consuming. And okay, it was a reward which was given by some utility function. So you see that here in this case, if you define the model in this way, it is quite natural to do it like that. And what you define is in fact a Markov decision process. So sometimes it is much more natural to use these disturbances interpretation instead of the Qn, this Qn xa of this Markov decision process xn, they are given by the in fact they are given by the Q and Z of I wrote it before. See, it is this one, this formula which is here. I don't know what I did. Okay, it is this formula here, which permit to relate the two different interpretations of the Markov decision process. Okay, and you have this formula. So sometime I will use one, sometime I will use some other one. Okay, good. So this is the presentation of what is a Markov decision process. So now I think I will show you. So what will be the goal now that what we will do and what we will do tomorrow? So we are interested in some optimization problem. So what we have is that you have this Markov decision process. So you have some stochastic process, xn evolving with time n, and this evolution depends on the action that you are performed, because you are changing the probability measure of your evolution of your Markov chain, depending on the strategy that you are following. And so what we will be interested in, okay, I will explain afterwards the technical assumptions that we are doing, but what we want to do, okay, is maybe it is better to write V0. Okay, I write it first, V0. V0 pi x is an expectation with the pi above. The pi above means that you are following the strategy pi. Okay, you are taking at each time the rule, decision rule F0, at time 1, decision rule F1, at time n-1, you are taking the decision rule Fn-1. And then this is the sum from k equals 0 to n-1 of rk xk fk of xk plus gn of xn. So this is the total benefit that you will get in expectation by following the strategy pi. At each time you get some reward, which is rk, will depend on the state in which you are, xk, on the actions that you are taking, which is fk of xk. And you have the final reward, which is G capital N of xn. And what is your goal? Your goal is to maximize this average reward. You want to find the pi, which is such that that the pi star, say some optimal pi star, some optimal strategy, that phi 0 pi star is equal to the supremum over all the strategy pi of the V0 pi x. So x is the initial state, okay? You start from x, so that is a given data. So you can try to optimize also over x, but for the moment we fix x, and we will try to find how to find this optimal pi star in order to maximize this total benefit that I can get. Okay, it is some optimization in average. And we will see that in order to do that, in fact, we have to, we will construct some algorithm in order to find the best strategy. And this algorithm will be some backward algorithm. So we'll start from the final time. We say final time, we have to do this action at time capital N, time n-1, we have to do this action, time capital N-2, this action, capital N-3, this action, and it will be backward algorithm. So we will start with the action at final time, and step by step, we will find the initial action that we have to take. And it is a reason for which we will have to introduce not only this V0 pi, which is the total gain that you get by following the strategy pi between the time 0 and the time capital N. We will introduce also this Vn pi x, which is the average by following the strategy pi of the benefit. When you start, okay, you can start from any initial time, but given that xn is equal to x, so at time n, small n, you are in the state x, and you look at the gain that you get between the time small n and capital N-1. So this is a generalization of this V0 pi, which is the total amount of money that you can get during all the stage 0 until capital N. So here I restrict it to the time small n, capital N-1. And okay, here, if you look at the notation, so here it is, in fact, I put some dot here to specify the initial condition. In fact, the initial condition is not important because you have a Markov process, and I'm starting only all these, the things which are here depend only on the process after the time n. So in fact, we can start from any initial condition. What is important is what is your condition, initial condition at time n. So in fact, it is here. It depends only on this guy. And so similarly to the thing that we introduced, the maximum over all the strategy of this reward, total reward, we introduce this VNX, which is a supremum over all the strategies between the time small n and capital N of the reward obtained during the time n capital N. And if you look at this formula, for example, you see that if you look at what is this V capital N pi x, so Vn pi x, so it is very simple because you see the sum here goes from small n to capital N minus 1. So if small n is equal to capital N, means that it is empty, so you have nothing, and you have Gn xn, which is a final reward, given that xn is equal to x, which is of course Gn of x. So it means that you see whatever the strategies that you are choosing, okay, at the end, the final reward at time capital N depend only on the state in which you are, because you cannot make any action. So it is very intuitive. So this Vn pi x is always equal to Gnx. So in particular, this Vnx, which is the supremum of pi, is equal to Gnx. And what we will see next time is how to construct some algorithm in order to, now I know what is the final value Vnx, and I know that it is this value. Now at time n minus 1, what is the strategy that I have to perform, which is optimal? Then we will find the optimal strategy, then we'll go to the step n minus 2, we will find some optimal strategy, and so on. And this will give you what we call the Bellman's equation. But just before, so I will not present the Bellman equation today on the algorithm, I will present it tomorrow. But just to say that here, if you want to make this thing well defined, you see you are taking the expectation of some quantities, so, or some conditional expectation. So you need to be sure that it is well defined. So there is some interability condition to impose in your system in order that you can perform this algorithm that I will describe tomorrow. So this it is called the interability condition. It is just some interability condition which is necessary to make sense of all these objects which are here. Okay, so what you say, Rk plus and Gn plus. So I recall you, but I denote by, if I have some function f plus, it's just f plus x, it's just some function, it is a max between fx and 0. So in order to make sense of this expectation, okay, so a priori this expectation could be infinite minus infinity. I mean, we impose that these Rk plus Gk plus Xn are well defined, are interable, whatever the strategy that you are choosing. Okay, so that if this condition, interability condition, is satisfied, of course, it makes sense to consider this kind of expectation here. And it makes sense also to consider this kind of values, which Okay, it's a case where you have a state space which is finite. Everything, you don't need nothing about the interability condition. But in the case where the state space is infinite, sometimes you could get something, some expectation which could be infinite. The supremum here could be also infinite. So you have to be a bit careful about this interability condition in order to make sense of all these things. Okay. So I think it is the presentation of the Markov decision processes that I wanted to do. And I think that, yes, tomorrow we will see this algorithm based on the Bellman's equation. And we'll describe this algorithm to solve this optimization problem. So I will come back tomorrow to that. Do you have some questions or comments about something which was not clear? This, no, it was completely clear. If you want that tomorrow I come back to something, I can do it also. If there was something which was not very, didn't make sense for you, I can do it again, repeat it, explain it different way.
I suppose I was a little bit lost at the end.
At the, where at the end, here or here or here? Or in this disturbance interpretation, or?
Well, I think that from this slide on, but I think just it is a lot of different notations, and I just need to sit down for some time and just look at it for a while.
Yes, it's true. Yeah, it's true that yes, this definition of the Markov decision process takes. You need a lot of ingredients to define them. It is not like just a Markov chain in which you are defining just matrix transition and then it is finished. Here you need to define a lot of action space and so on. So, but we will see in some exercises and some examples more, some examples in which it will be, okay, will become more natural, but it will take some time to adopt all this notation. I agree that it is a bit difficult at the beginning. So effectively, you have to sit and to read exactly all this definition. But we will see some examples. So I hope that you will be step by step. It will become more clear.
And so, at what time do we gather tomorrow?
Yes, tomorrow we say that it was 2 p.m. Yeah.
Yeah, I suppose. Yeah.
It is what I in the email that I sent. It is what I said. So 2 p.m. is okay for you? Yeah.
Yeah, for me 2 p.m. is good.
Okay.
And Paulina is not here. Paulina is not here anyway. But I mean, okay, if we are agreed to 2 p.m., let it be 2 p.m. I suppose. Yeah.
But she's aware about this because she sent me some email and so she knows that it is at 2 p.m. But I don't know. Maybe she will. Anyway, she is everything is recorded, so it should be okay.
Okay.
Just it's better to attend to ask questions.
Yeah. It's just about like you feel that you are into the discussion when you are present. Yeah. Yeah,
but it's good that you ask questions because otherwise I don't know things which are not clear and things which are too easy or. But okay, if I agree that this part is a bit difficult because we introduce all the notations and you will need some time to digest them. But we will make several examples or computations on these on different models of Markov decision processes. So at the end, it will become quite usual, I hope.
Okay, thank you.
Okay,
Excuse me.
Yes.
Can you please recommend some literature on Markov decision processes?
Yes, I will. I will send you some by email. I will send you some references. Yes.
Thank you.
Okay, so we will see us tomorrow at 2 p.m. for you. Okay.
See you.
Bye bye.
Goodbye.